Hello and welcome to this episode of Math with Martinez. We are in our Pre-Cal Unit 2 where we're looking at the composition and inverses of functions. And the focus of this lesson, our objective, is to determine an inverse function when it exists for a given function over its domain or a subset of its domain and represent the inverse using multiple representations. So let's go ahead and jump to those notes and we will get started with determining our inverse functions. Let's recall that for an inverse relation, if relation, and call it R, contains the ordered pair AB, then the inverse relation would be denoted like you see here with this little -1 as like the exponent, but we would read that. You would read this. You would read that as R inverse. And it would contain the ordered pair BA. And what I want to highlight here is just exactly what happens. Notice what we have to begin with. We have A, and then its partner is B. Your A is an X value and B is a range or a Y value. And for the inverse, what ends up happening is those values are switched or reversed. And that is what occurs with an inverse. Your domain and your range, or said differently, your X and Y values are reversed. So if we're looking at now more specifically at inverse functions, the inverse of a function f of x is written like this, f inverse of x. And it's just like you saw for the inverse relation up above. It's got the matching function or relation letter, but then you're going to be raising it to what looks like a -1 power, and that's just the way to denote an inverse. Now, big and super important idea here, steps to find the inverse of a function. Here they are, the steps to find the inverse of a function. There are 4 of them. The first is going to be to replace. You're going to be replacing the function notation, which is usually f of x, with a y. Then, once you've replaced that function notation with that dependent variable y, you're going to switch your variable positions. You're going to switch the x and y in the equation. Next, you'll tackle step number 3, which is to solve for y by using opposite operations. And then lastly, once you've solved for y, you're going to rewrite that equation using the inverse function notation, f inverse of x. So replace, switch, solve, and rewrite. Those are your key words for the 4 steps when finding the inverse of a function. So let's think about here this example together and use these 4 steps to help us do that. We're going to find the rule for the inverse of this cubic function f of x, which is equal to the quantity x minus 1 cubed plus 1. So let's go ahead and begin. Step number 1 is going to be to replace f of x with y. So I'm going to come in here and I'm going to replace, and instead of it's saying f of x, what we're going to write instead is y. And then the rest of it, just like it was, equals x minus 1 cubed plus 1. So that's your first step. Then step number 2 is going to be to switch the x and y. So where there was a y, now it is x. And where there was an x, we're going to switch it and write the y variable. Notice nothing else changed, just x and y switched. If there would have been a number like right here in front of the x, anything right here, it wouldn't move over to the other side. No, it stays, just like this parenthesis stayed, just like the -1 stayed. All the rest of the equation stayed the same. It's just the variables that switched. Then step number 3, we're going to solve for y using those inverse operations, reverse PEMDAS. So can we undo any adding or subtracting? Because remember, you're always going to do PEMDAS in reverse order. Whenever you're solving, you're doing PEMDAS in reverse. So any adding or subtracting we can do? Absolutely. We can go ahead and subtract 1 on each side. That'll give us x minus 1 equals the quantity y minus 1 cubed. That was our first step in solving, but y is still not by itself. Our next step, because this group is cubed, I can't undo the -1 inside that group. I have to undo the group. To undo a cube, I'm going to have to cube root each side. So I have x minus 1 being cubed rooted and y minus 1 cubed being cubed rooted. Now, that's going to eliminate your cube root on the cube root, and the cube will eliminate each other on the right side, and I will be left with the cube root of x minus 1 on the right. Our final step is just going to be to add 1 on each side, and that gives us the cube root of x minus 1, then plus 1 after that cube root, because it was an operation we did after, equals y. Y is now all by itself, so we can go ahead and complete this process writing it using that function notation. That's to replace the y with f inverse of x, and then write the rule. The rule was the cube root of x minus 1 plus 1. That, ladies and gentlemen, would be our final answer. That is the inverse of our function f. So there you have it. That is one example where we are finding the inverse of a function. Now, an important thing, part of our objective is to identify when we even would have a inverse for a given function. And the way that you'll know if a function has an inverse is using the horizontal line test. The horizontal line test is used to determine if a function's inverse will be a function. So when I take and run this horizontal line across this graph right here, if I do that, let me just kind of actually show you this happening. If I run this line across this graph, notice it's only ever going to touch 1 point on the graph at a time. And because it's only touching 1 point at a time, this function is going to have an inverse, which makes sense. Yes, of course, this linear function will have an inverse. So we can say passes and I like to abbreviate it, horizontal line test. And then we can say, so the inverse is a function. And you would actually go ahead and write it as, if it was f, then you'd write f inverse of x. But take a look at this next example. Do you see how for this example, even just at that moment that I just highlighted, this horizontal line touches way more than just 1 point on the graph at a time. It's touching a lot of points. So this graph, this cosine function graph, which we'll study later this year, fails the horizontal line test. So the inverse is not a function. We actually would not be able to find the inverse of this graph unless the domain was restricted so that it passed this test. And lastly, this is one that a lot of students can easily miss. So I just want to show you for this function. This is a reciprocal or rational function, and it can be a little bit deceptive here. But if you run this, it actually only will touch one point on the graph at a time. Even though it gets very, very, the slope there, if you're looking over like towards this end or over here, it gets very flat. It never actually gets completely horizontal. So we're only ever touching one point. So we can find the inverse of a reciprocal or a rational function like this one, this reciprocal function. So again, for the first and the third example, we could find the inverse. But for example 2, we would not be able to find the inverse for that function unless something was done to restrict that so that it passed your horizontal line test. Now, this is a process that we studied in Algebra 2, the idea of composition. And so let me remind you that if a relation and its inverse are functions, like we would see here with example number 1, if you found its inverse, it would also be a function. And if you did example 3, its inverse would be a function. If two functions are inverses, then this is what will be true. When you take f and compose it with f inverse, or if you take f inverse and compose it with f, the result every time should just be x. That is the indication that they are inverse functions. So let me demonstrate that for you here. Here's my green function, and here's going to be my blue function. We're going to compose these to demonstrate that they are, in fact, inverses of one another. So we're going to take g of h of x, and our hope is that it will equal to x. That's the goal. If it equals x, then they're inverses. So let's go ahead and rewrite this. We know that g of h of x is the same thing as writing g of h of x. So that h of x function is what's going to go inside of your g function. So that means my g function is 4, and then we're going to put an input minus 1. That input is the whole h function, just like so. Now let's go ahead and simplify and see if we have inverses. Because this group is multiplying by 4 and the x minus 1 is also dividing by 4, it is only now, and because it's both multiplying and dividing, that the 4 that's multiplying and dividing simplifies to 1, and we're left with x plus 1, the blue portion in the numerator, and then minus 1, which of course simplifies just to x. So that's looking good. We did compose the functions and the result was just x. And to prove it to you, let me also go ahead and do the composition h of g, the hog composition. Sorry, I couldn't help myself. That's the same thing as h of g of x. That g function, our green function, is the one that's going to go inside of the h function. So set up your h function. My h function is going to be a quantity plus 1, or the input plus 1, all divided by 4. And in that numerator is where we're going to plug g, so that's 4x minus 1. Now, what I saw a lot of students doing incorrectly earlier in this unit is canceling out the 4's right now. But we cannot do that because this 4 is not multiplying everything in the numerator, so we can't divide it out. It's only if the 4 is multiplying and dividing. This 4 is not multiplying by everything, so we cannot divide it out. We cannot simplify that, or at least not yet. But what I am seeing is that really all I've got is in my numerator, I can drop those parentheses because I'm just adding the 1 at the end. Now I've got a adding 1 and subtracting 1. So that really is quite beautiful because these two can simplify their additive inverses. And now look at that. That 4 is multiplying in the numerator. That's the only thing that it's doing. It's multiplying with everything else in the numerator. So now we can simplify those. And it is just x. So they are inverses. G and H are inverses because the result of the composition each time was just x. So that is how you can verify two functions are inverses of one another algebraically. That is just about it. There's one more thing that I want to show you here, and it is how to check graphically that two functions are inverses. So let me clear these out. And I want to show you when I graphed those two functions what that would look like. And the second one. All right, so you see these two functions here, when graphed, they actually have a really unique relationship with one another. We studied here at the start that what happens is your points reverse each other. And so because they reverse each other, what ends up happening is these two lines are actually perfect reflections across the line y equals x. Oops. You see how I've graphed that green line, the y equals x line, and the red and the blue function, your g and h, they are perfect reflections across that line. What was the point -1, 0 right there on the red graph is going to be reflected, and it's actually going to be 0, -1 on the blue graph. They both cross the green line at exactly the same point, and every other point is just a perfect reflection so that the x and y's flip or switch. So that's it. That's how you can check graphically. Composition is how you check algebraically. Make sure that you run a horizontal line test before finding the inverse, because if it doesn't pass, like we see here, then there is not an inverse. And your 4 steps to finding an inverse when the inverse does exist. That's it for this video. If you guys had any questions, please take a moment to share those now. And until next time, stay fired up, y'all.